Hello, this is Michael Sulak, and in this video we're going to be doing a hypothesis test. And specifically, we're going to be doing one for a population proportion. And this video isn't going to do a lot of talking about the theory behind hypothesis tests. It's just going to focus on how you do one. And specifically, we are going to be using what's called the p-value method. There's another method called the critical value method. I personally prefer the p-value method. It is what you might see more often in scientific literature. For me, it just is simpler than the critical value method. So here's the problem we're going to be looking at. I'll read this, and while I'm reading it, I'm going to highlight anything I think is especially important. This starts out with, according to the U.S. Census Bureau, in 2009, 7.8% of Americans had a travel time to work of more than 60 minutes. So that's talking about their commute time. An urban economist believes that the percentage of Americans who have a travel time to work of more than 60 minutes has increased since then. That's important. I'm going to highlight that. She randomly selects 80 working Americans and finds that 11 of them have a travel time to work that is more than 60 minutes. Test the urban economist's belief using an alpha level of 5%. First of all, this paragraph is talking about a certain population, a group of individuals or observational units. And in this case, we can assume, although it's not stated, that that population is all working Americans. You can imagine there's a lot of working Americans. There's 300 million people in America, and a lot of them are working, so this is likely at least tens of millions of people. Hard to know about. And I think it's a good idea to think about what the variable is that we're looking at here. The variable is whether or not these working Americans have a commute time of over 60 minutes. Either they do or they don't. So this variable is categorical. And there's a parameter of interest in this problem. There's a number, parameters are numbers, that describes our population, that describes all working Americans. And because our variable is categorical, our parameter is going to be a proportion. Although there's some numbers in this problem, our data is categorical. It's indicating either yes or no for their commute time. So the parameter is going to be a proportion. It's the proportion of all working Americans that currently have a commute time over 60 minutes. And we don't know this. We know what was happening in 2009, but we don't know what's happening currently. We are going to try to figure out what we can say about this number. So this is our parameter. It's the proportion of our population. This could be given in symbols as a capital P. And let's look at what this economist is trying to figure out. She wants to know if the percentage of Americans who have a travel time to work of more than 60 minutes has increased since 2009. So the first step of conducting a hypothesis test is to write down what's called the null and alternative hypotheses. And a lot of times the null hypothesis will be given as an H with a 0 down here. And the null hypothesis is always about our parameter of interest. If we're talking about the proportion of all working Americans, and we have this capital P, our null hypothesis is about that P. And our alternative hypothesis, an H with either maybe a 1 or an A subscript. I like using an A subscript. It reminds me that it's the alternative, is also about this P. What we're doing in this case is we're comparing this proportion to this 2009 value. And sometimes you might see this described as P naught. It's a number that we want to compare our parameter to. So if we want to know, has it increased? Has the proportion of people with a commute time over 60 minutes gone up since 2009? The research objective always appears in the alternative hypothesis. If it has increased since 2009, then it would be bigger than its 2009 level of 7.8%. And the null hypothesis is always a statement of no change. There's nothing going on. Null is like nothing or nada. And so we always use an equal sign here. And we always use the same number in the null and alternative hypothesis. So we're basically covering all the possibilities. Either it has increased and it's more than 7.8%, or it has not increased. So these are the null and alternative hypotheses we will use to test this researcher's question. Now that we have our hypotheses, we are going to calculate what's called the test statistic. And because we're doing a hypothesis test for a population proportion, our test statistic is a z-score, and the test statistic has a formula that looks like this. So we need to know what these numbers are. Let's start with this P naught. The P naught is just the number that we were comparing our parameter to. It's the number that appears in our formal hypotheses. And we have to be a little bit careful because when we're working with numbers, we want to use the proportions and not the percentages. The decimal equivalent of this percentage, that's what we'll use in this formula. So what else appears in here? We have N, that's our sample size. That's the number of individuals that were measured in this problem. And it's given to us right up here that she randomly selected 80 working Americans. Our sample size is 80. And our P hat is a sample proportion. It's the proportion of these 80 people that in this case had a commute time of over 60 minutes. So she selected 80 people. That's going to be the bottom of this fraction. And of those, 11 of them had a commute time of more than 60 minutes. So our sample proportion is 11 over 80, and if I work that out, I get 0.1375. So the whole idea of this hypothesis test is to see if we can make an inference about the entire population. We were wondering if the proportion of American workers with the commute time over 60 minutes is more than 7.8%. And we have a sample proportion that is more than 7.8%. It's 13.75%. What we want to know is this big enough? Is it large enough to conclude that I think it gives me evidence that the population proportion is over 7.8%. Let's go ahead and put these numbers into our formula here to calculate our test statistic. So we're going to get z equals p hat, that's 0.1375, minus p naught, which is 0.078. Then we're going to divide that by the square root of p naught, which is 0.078, divided by 1 minus p naught, and then we divide all of that by our sample size. So if I keep going, I would do this subtraction in the numerator and I get 0.0595. And I'm going to be careful about doing this square root. Maybe I'll just do this part all at one time in my calculator. So I'm going to have the square root, and when I do this part on top of that fraction, I end up with 0.0711916. And that's still divided by 80. So I'm just going to carefully complete this bottom part. So I still have my numerator So I'm going to take what's underneath that square root, and when I divide these two numbers, I get a really small number. It looks like scientific notation in my calculator. It has an E in it. But if I take the square root of a really small number, it gets bigger. And so the bottom of this fraction ends up being 0.02998. And there are some more decimals, but I should have enough accuracy if I use 4 significant digits. So now I'm just going to finish calculating my test statistic, and I get 1.98. So that's my test statistic. There are also computer programs, or your calculator has a function potentially that will allow you to find this. And you might not have to do it by hand every time. But I like knowing where things come from. And so the value of our test statistic for this problem came from that formula. And there is an interpretation of this. It's how far from the mean was the result that we got, our p hat of 11 over 80. If the null hypothesis, if this statement is actually true. So if 7.8% of working Americans currently have a commute time more than 60 minutes, the result of getting 11 out of 80 that have a commute time of more than 60 minutes is about 2 standard deviations above what we would expect. So that's a little unusual. And what we're going to do next is find what's called the p-value that quantifies exactly how unusual it is to be about 2 standard deviations above what you expect. And this is a z-score, our test statistic is. And z-scores have a standard normal distribution. I can write the idea that it has a standard normal distribution using these symbols. It's distributed normally, and that distribution has a mean of 0 and a standard deviation of 1. And so the p-value is the area under this distribution that corresponds to our alternative hypothesis, in this case greater than. So our p-value, if I draw a standard normal distribution, so what we want to do is label our test statistic on this distribution. So if this is 1 standard deviation, 2 standard deviations is about here, and we want to know the area that's greater than our test statistic. The p-value for this problem is the area greater than 1.98. It's the area up here in this distribution. And we don't know that, so we're going to find that. If you have a TI calculator, you can use the normal CDF function to do this. You could use a normal table if you want. You could use some computer program to find this out. If I do normal CDF, we are getting a result of 0.239. That's what's called our p-value. And then the next step I always do is make the decision. The decision is always either reject the null or you don't reject the null. It's one of these two things, and the way you decide which one to do is we take our p-value, which in this problem is 0.0239, and we compare it to what's called the alpha level, which is given to us up here in the problem. It says use an alpha level of 0.05. The smaller the p-value, the more evidence you have against the null hypothesis. To make our decision, we compare the p-value to the alpha level. And if it's small enough, if it's less than our alpha level, which it is in this case, then we have enough evidence against the null. Our decision is going to be that we are going to think that the null is not actually true. We're going to reject the null hypothesis. And you always reject the null hypothesis if your p-value is less than your alpha level, which it is in this case. If your p-value was more than alpha, you would not reject. So our decision is going to be to reject the null hypothesis. We had a result that was rare enough that we think this is not actually true. And just to talk a little bit more about why the p-value being small says that we reject. When we calculate the test statistic, we assume the null is true. We assume that the proportion is actually 7.8%. And so when we find the p-value, which results from our test statistic, this is the probability of seeing our result if the null is actually true, because we calculated this assuming that it was. So the smaller this is, the more evidence we have that the null isn't actually true. And so when the p-value is small enough, then we end up saying our results were so unlikely that we think what is probably the case is that the null hypothesis is not actually true. So the decision is to reject the null hypothesis for this problem. And the last step is to state a conclusion, to talk in relatively not scientific language about what does all this mean regarding what this economist wanted to know in the first place, whether or not commute times have increased since this 2009 level. So we always want to start out with something regarding that the result we're about to state corresponds to the data that we collected. And if we had collected different data, we might have gotten a different result. So we'll say according to this data, and now we just want to say whether or not we have reason to support her claim. She thought that the percentage of Americans who have a travel time to work of more than 60 minutes has increased. And what happened? Well, we had a null that said it did not increase. And we rejected that null hypothesis. We said, we don't think you are true. What we think is true is actually the alternative. So in our conclusion, we're just going to state the alternative. We're going to have a sentence really similar to what appears up here. According to our data, we have significant evidence that this happened, that the proportion of all working Americans, I'm so long that I'm going to need a little bit of room. We have evidence that the proportion of working Americans that have a commute time of more than 60 minutes has increased. Interestingly, when we state our conclusion that we think commute times have increased, we could be wrong because we're making a statement about a very hard to know thing. We're making a statement about all working Americans. And our data says that this proportion has gone up, but there's a chance that it didn't. You could always be wrong, but statistics is all about using the data that we had to make the best conclusion that we possibly can. And that's what a hypothesis test does. It tests some belief, it tests some hypothesis using data and makes a statement about what we think happened with our parameter. And in this case, we do think that commute times have gone up since they were measured in 2009. This was doing a hypothesis test with the p-value method. I always recommend doing these 5 steps: stating the hypotheses, calculating the test statistic, using the test statistic to find the p-value, comparing the p-value to the significance level, the alpha level, to make a decision, and then using the decision to state a conclusion. So that was an example of a hypothesis test for a population proportion. My name is Michael Sulak. I hope this video was helpful, and I will see you next time.